And I've got to get my tablet set up. Just give me a second. All right, let's see.
Recording stopped.
Okay, so let me get my notes together here. All right. Okay, I think I'm getting a little
Recording in
organized here.
progress.
All right. So, how's everybody doing? Okay.
Good.
All right. So, well, here, let's just talk a couple minutes about the class. All right. So this is actually 4 different classes that are all combined or cross-listed. There's Math 301, and then there's also Math 601. So that's sort of a graduate version of the same class. And then it's cross-listed with physics. So there's also Physics 301, and then a 600 level graduate version of that, which is Physics 605. And somehow along the line, those different sections all got different titles. so some of them are called, mathematics for the physical sciences, and some of them are called theoretical physics, and one of them is called mathematical physics. And so there's a lot of different titles. And it's ironic because I don't think any of those titles actually contain the words partial differential equations, which is actually the topic of the class. Partial differential equations and Fourier series. That's the main topic of the class. So anyway, I don't know how that titling all came about, but I think, of all the titles there are amongst the different sections, I think mathematical physics is a good title for the class. Mathematical physics refers to a certain set of topics in mathematics, and including things like partial differential equations and Fourier analysis. Although there's more to mathematical physics than just PDEs. There are other topics that are also considered mathematical physics, but we're going to focus on PDEs and Fourier series. Now, I should also point out, okay, so some of the students in the class are math majors and some of the students in the class are physics majors. Now, I should also point out though, obviously, if you're a physics major, then this material is directly relevant to your studies in physics and represents basic material that it's fair to say probably every physicist has studied at some point. If you're a math major, then this material is a topic in mathematics, which may or may not be in the direction of the specialty that you end up going in. That just depends on where your interests lie and where your mathematics takes you. However, I'd like to just point out that the mathematics that we're studying, and in particular the applications that we're going to be studying to PDEs, things like the wave equation and Laplace's equation and the heat equation, that mathematics is actually just as applicable to other areas of applied mathematics besides physics. So one of the great things about the subject of differential equations, and you probably learned this or got a taste of this when you took your ordinary differential equations class, which is a prerequisite to this, is that when you write down a differential equation and you use it to model a certain phenomenon, and you set up the equation, and then you do the mathematics to solve the equation, you get the solution, and then that tells you about your model. But that exact same equation or that exact same mathematical model also models some other situation in some completely different area of science. So you might write down a differential equation that models the growth of some stock or bond or derivative security in a field of mathematical finance or economics. But the very same equation, the very same mathematics might be used to model population growth or ecology or something like that in the field of biology. So the point is, if you're more of a mathematician, or you're more just studying this because you want to learn the mathematics, and you don't necessarily know that much about physics, or you don't particularly care about physics, just keep in mind that when you learn to solve the wave equation, and you learn how to understand the vibration of a guitar string or something like that, the same mathematics also models an equation that models a derivative security in mathematical finance or something in a completely different field. So it's like, yes, it's mathematical physics, but at the same time, it's mathematical fill in the blank. Okay, so just keep that in mind. And then, of course, again, as I say, if you are studying physics, then yeah, you are interested in the vibration of a vibrating string, or a stretched membrane, or the diffusion of heat through a surface, or something like that. The Black-Scholes equation, which is the most famous equation in the field of mathematical finance, which was discovered by Black and Scholes sometime in the 1970s, and is used to model derivative securities, which forms the basis for modern options and futures trading and all that. The Black-Scholes equation is actually just an example of the heat equation. So the same equation that Fourier and Dirichlet and people started studying in the 1800s to understand the diffusion of heat through a rod in the one-dimensional case, or some sort of surface in the two-dimensional case, or whatever. That same equation, kind of jazzed up a little bit with some probability theory thrown in, is actually the fundamental equation of mathematical finance, starting in the late 20th century. So anyway, so I just wanted to kind of make you aware of that. All right, so let's see. I sent out an email to everybody a few days ago, and then I sent out something from Blackboard about a day ago or so, and then I just sent out the link, the Zoom link, through Blackboard just like an hour ago or something. If you're here, then that means you probably got one of those, or at least you went on to Blackboard or something. Is there anybody who didn't receive any of my emails? I guess that's the question. Is there anybody who didn't receive the emails? Nobody. Oh, okay, all right, that's good. Here, hang on a second. I have to do this do not disturb thing. Okay, all right, well, good. All right, then I'll proceed. And if at some point somebody finds out that they're not getting the emails, let me know. All right, so the emails contained a link to the web page for the course. So hopefully you looked at that. That has basic information about the course. Does anybody have any questions about that? Any questions about the basic information that I sent out about the course? No questions. All right. Okay, here, let me check I want to check the chat. Okay, so I don't see anything in the chat. All right, okay, so let me point out something about class. Yeah, do you want us to use the chat? Yeah, okay, so here's the deal. You I think I've got, I've got you muted by default. I select this option that says mute everybody by default upon entry. So you come in and you're muted, but you have the ability to unmute yourself. So if you want to ask a question or speak up or something, just unmute yourself and speak up. And that's fine. So I would encourage you. That's actually sort of my preferred method of fielding a question, is somebody just speaks up and says, wait a second, I don't see what you did there. Why is that true? Can you go back and do that again or whatever? But you can also chat a question. I'm not so great at monitoring the chat in real time. It especially when I share my screen and open my tablet, which I'm going to be doing, then the tablet sort of like fills the whole screen, and I think I have to kind of do something extra to take a look at the chat. So I'll try to sort of check the chat as I go along, but it's hard for me to kind of be reading all the questions in the chat in real time. So if you put a question in the chat, I'll try to see it, but I might not see it right away. If somebody puts a question in the chat and I haven't answered it because I haven't seen it yet, and you happen to notice that there's a question in the chat, and you're not afraid to speak up, then by all means unmute your microphone and just say, Professor Thompson, somebody has a question in the chat. Can you look at that? And then I'll go over and I'll look at the chat and I'll see the question. And then same thing goes for raising your hand. You can raise your hand. That's another option. But again, that requires that I sort of be looking over at the class list, which again, I mean, I can see it pretty clearly now. And when someone raises their hand, their name kind of rises up to the top of the list. So I can see that too. But again, when I full screen and I have my tablet going, that's kind of hidden or something. And I have to actively click on something to kind of bring that up. So again, same thing. If you can raise your hand, but I might not see it right away. So, I think the best thing is just to kind of unmute your mic and ask a question out loud, just like if we were in a regular class or something. But I am noticing, okay, is attendance mandatory for this class? Are you going to take attendance? Well, no, I don't know. Attendance isn't mandatory. Attendance has never been if there's no raise hand feature enabled in this meeting, so we can't use that. Well, is that really true? Because in my version of Zoom, a lot of people say the raise hand thing is in the reactions tab, but that's not true on every version of Zoom. In my version of Zoom, I don't have a raised hand in the reactions tab. But if I go up to my name in the participant list and, oh, actually, wait, hang on, I'm not seeing it. Okay, all right. Oh, that's interesting. Okay, so maybe I don't have, okay, maybe wait, hang on. Yeah, okay, I see your point. I guess maybe I don't have hand raising enabled in this session. Okay, all right. So I'm gonna have, I'll try to fix that for, yeah, I'll try to fix that for next time. All right, okay. Let's see, raise hand is listed under the reactions tab. Okay, so some of you have raise hand under your reactions tab. Is that right? Is that what I'm getting? Yeah, okay, all right. So I guess okay, so it's not a question of my end, it's a question of what your thing is set. So maybe you should check your Zoom version. Maybe if you update your Zoom version, then you'll get a raise hand option in your reactions tab. Let's see, Discord server, would anyone object? Well, I certainly don't object. it's quite standard actually, especially during COVID with all these online classes and whatnot. I feel like in just about every class I teach the students, someone's setting up a Discord server for the class. So I was kind of assuming that would happen. But anyway, yes, I do object. We have one already. Okay, all right. Okay, all right. Well, okay. So if there's one already, then please, share that with everybody else so that everyone can get on that. Okay. All right. Let's see. What else? Does anybody have any questions about the class, just like the way the class is run or the way the class is going to get set up or anything? Any questions at all? Any questions about anything?
I have a quick question about Mathematica.
Oh yeah, right.
So, I mean, you can just talk about it, but I've never used it before. So I was wondering how involved we're going to be with it.
Okay, well, I want to use it. I plan to use it, but I haven't really, I didn't really say much about it in the, I didn't really say much about it in the information that I sent out or anything like that. So I'm going to be sending out a little more information. Well, not a little, I'll be sending out more information about it as we go along. Basically, for now, what I would just say is, I would say get it. Just contact. If you don't have it already, you should be able to. Here, just hang on a second. You should be able to get it. CUNY has a site license, and it's available to students. And so I believe that you should just contact the help desk at ICIT and tell them that you need to get a copy of Mathematica because you're taking math or physics class that's using it, and they'll tell you what the steps are to get it. So just do that. And if you have any problems or questions about that they can't answer, let me know and we'll pursue it. But typically, the last time I taught this class, I've taught this class the last 2 years in a row. So this is my third fall semester in a row teaching this. And the previous 2 times, I just said to the students, we'll use Mathematica a little bit, and if you want to get it, get it. And the students just got it. So I didn't have to really do anything myself. So just try that, and then you should be able to just get it. Let me know. And then I'll use it a little bit in class for some demonstrations and whatever. And then after a while, not right away, but at some point, a few weeks into the class, maybe I'll start assigning a few homework problems that involve you using Mathematica. So I'm planning on kind of, using it gradually as we go along, but it's extremely, powerful, and it's extremely useful. And this is, and PDEs and Fourier series and whatnot is a very natural place to use it. Okay. All right. So I know, yeah. Okay. Oh, link to instructions for getting Mathematica. Oh, I see. Okay. So they actually have, yeah, they have, right. So right. The website should have, the CUNY website and perhaps the Hunter website should have a list of software that's available and tell you how to get it. Okay, great. All right. Any other questions? Any questions about anything at all?
Professor?
Yes.
So we're using the textbook that you want. The homework problems, they're coming directly from the textbook. Is that correct?
Yeah, exactly. Yeah, exactly. That's right. So the textbook is Partial Differential Equations by Nakli Osmar. It's this paperback thing. It's published by Dover. It's this reddish brown color. And it says at the bottom, third edition. So the first edition was published by, I believe it was Prentice Hall. And the second edition came out, and that was Prentice Hall. And then Prentice Hall sold it to Dover, and now it's published by Dover, and they're calling that the third edition. I have yet to see any difference between this third edition published by Dover and that second edition published by Prentice Hall, which has, or maybe, well, anyway, I'm not aware of any differences between, yeah, that's the picture of it. Yeah, that cream, that sort of cream colored thing. Yeah, that's that thing right there. Yeah, does that say second edition on it? Yeah, okay. So I'm not aware of any difference between the third edition and the second edition. Usually when the publishers upgrade to a new edition, they make some gratuitous changes in order to make the new edition different, so that students will be forced to ditch the old edition and buy the new edition. That's how the publishing companies keep their revenue stream going. But the changes oftentimes are gratuitous and not significant in terms of the content of the book, but they're just designed to kind of make it annoying to keep the old edition. Like they change the homework problem numbers around and things like that. In this case, I don't think that really happened, because the change wasn't an upgrade of an edition by a publisher. It was a selling it over to a different publisher. So when Dover took it on, Dover Publishing Company does that. They take on a lot of books that the other publishers don't want to have anymore. So when Dover took it on, I don't think they changed anything. So the point is, the point I'm getting at is, if you have the second edition instead of the third edition, that's probably fine. I think you could probably just use that. I don't think there's going to be a problem with the numbering of the homework problems. We'll see. If someone finds a difference, then please point it out, and then I'll know about it. But anyway, officially, technically, the book is the third edition, and the homework problems are, for the most part, going to come out of the book. Although, when I assign some homework problems using Mathematica, they might come from a different source, because I don't think the book is really geared, it's not tied towards Mathematica, I don't think. Anyway, so, all right, okay, another question. Okay, I've got the grading rubric and all of that. Oh yeah, okay, so one final thing. So just to kind of get everybody oriented. So we're essentially using 3 different platforms. We're using Zoom for the class, the actual class periods, the class meetings. There's a web page which is on the math department web server on my homepage. Link, you can get to it from my homepage, which has information about the course. And then the third thing is Blackboard. Okay, so I'm not actually planning on posting a lot of information on Blackboard. And when I do post information on Blackboard, it's probably just going to be a subset of the information that's posted on the web page. So you're going to go to the web page as your primary source of just information on the course. Blackboard for us is going to be used primarily as the vehicle for you to upload homework and exams, right? You're going to be uploading homework. When you submit the homework, you're going to be uploading it. And when you do the exams, you're going to be uploading them. And there needs to be a place for you to upload them to. And that's what Blackboard is good for. That's going to be the primary way we're going to use Blackboard. So there will be links on Blackboard in the homework and exam sections where you'll go to click to upload the stuff. And now the way it'll work is I'll assign homework, and then you're just going to do the homework the old-fashioned way. Just do it on paper, just take a pen or a pencil and paper and just write out the homework on the paper, and then scan it and upload it. And I'll write down a few more instructions about the scanning and uploading. But basically, when you scan it, the most important thing is you just want to scan it and save it as a PDF. Don't save it as a JPEG or some other picture file and upload that. Please scan it and save it as a PDF and upload a PDF. And also get it as one file. Don't for a given homework assignment or for a given exam, don't upload like 6 different PDF files. Just scan it, save it as a PDF in one file, and upload it. You can get, if you have an iPhone, there's lots of scanning apps for the iPhone, and maybe you actually have an actual scanner. Now, having said that, if you do have a way of digitally producing the homework assignment, then that's fine. Like if you use LaTeX, for example, then some students use LaTeX. I use LaTeX all the time. I write everything in LaTeX. So all my research papers, all my quizzes, all my exams, everything is in LaTeX for me because I've been using it all my life. But students, you may or may not use LaTeX. But if you do use LaTeX or something like that to write out mathematics, and then it's all digital, and that's great. You could just produce a PDF and upload it. So you don't have to use paper and a pencil if you're producing things digitally. But whatever you do, at the end of the day, your end product is going to be a PDF file, which you will then upload. So that's for that'll be for the homework and for the exams. Okay, anything else? All right. Well, so I want to just launch into a problem. Okay. So the way I'm going to introduce, I'm not going to introduce this subject with a lot of formal definitions and statements of theorems and this, that, and the other thing. I want to actually just introduce the subject by just stating a problem and just going through how we would solve this problem. All right, and this and that, and there's a lot of things that are sort of contained within this that will launch the topic. Okay, so I need to open up my tablet software, and I'm going to share my screen, and if it wasn't online, like before COVID, we'd be in a classroom and I'd be writing on the board and you'd be thinking, oh my God, this guy has the worst handwriting I've ever seen. Well, unfortunately, writing on this tablet doesn't make it any better. So now it's the worst handwriting you've ever seen, but on a tablet. I don't know what to say. You'll get used to it. How's that? You'll get used to it. All right. Can everybody see the whiteboard? No, because the screen sharing stopped.
Not anymore.
Okay. Can you see the whiteboard now?
Yeah.
Yes.
Okay, good. All right. And you can hear me all right?
Yes.
All right, let me see. There's a question in the chat. Let's see. Can we use Mathematica or MathCAD? Let's see. Oh, during the exam, do we have to turn on the cameras? Yes, I would like you to have your camera on during the exam. I would like to have the cameras on during the exam. You're not required to have your camera on during class. Oh, yeah, actually, yeah, let me okay, I'm gonna stop sharing for a second. I'm just gonna make a comment about the cameras on. You're not required to have your camera on during class. And so that's fine. I'm not gonna say anything about it except for this initial comment. But I just have to say, if people do have their cameras on, it does feel more like a class, right? I mean, it's like, so, you know, from my point of view, when I'm talking or explaining things, you know, normally in a classroom, when I'm standing at the board and I'm talking about stuff, I'm looking out, I'm seeing people's faces. You know, some people look happy, like they understand everything. Some people are scowling, like they're confused. You know, sometimes I call on a person and say, hey, you look confused. You know, is there something, you know, do you have a question about this or whatever? You know, it's just, it's like an interactive thing. And this online teaching, you know, one of the problems with this online teaching is you're just staring out to a giant array of gray rectangles. and you know, you're not getting any interaction. You're not, you know, so that's all. I'm not trying to lay a trip on you. You're not required to have your camera on. I totally get it. But you know, it just, when people's faces are there, it does feel more like a class. So just tossing that out. Okay. Anyway, but let's make it a requirement for exams, just, you know, for security reasons. Okay, all right. So getting back to, okay, so we got the whiteboard here. So now so here's the problem I want to look at. It's the problem of a vibrating spring. I'm sorry, a vibrating string. Okay, so I'm just gonna describe the problem, and then we'll talk about how we would solve it. Okay, so imagine that you have a string, and it's pinned down at two ends, and then the string goes between the two ends in some fashion. And if I call this the horizontal axis, the x-axis, then let's say this is 0 and this is L. So the length from this point to this point is L. And then in the vertical direction, we'll have an axis, and I'll call that U. And so we have a function U, which is a function of two variables, x and t. So x is the spatial position along the horizontal axis, and t is time. And then u of xt is going to be the position of the point on the string at the coordinate x at time t. So in other words, for each t, we have a graph of a function on the interval from 0 to L. And then as t changes, that graph changes. That's another way to think of it. It's just a function that depends on, it's a function defined on the interval from 0 to L that depends on t. Okay, but we're going to think of this as a model for a string that is stretched between two endpoints. And the string is under tension. Okay, so if the string was completely not moving, if the string was just stationary and not moving at all, it would just be a straight line segment going from 0 to L. Okay, but what we've done is we've grabbed the string and we picked it up and put it into some position not constant equal to 0, and then we let go, and the tension of the string causes it to then vibrate. Okay, so the example to have in mind, of course, is a guitar. Just think of a guitar string. A guitar string is an elastic string that's under tension, and it's attached at the bridge of the guitar at one end, and it's attached to I'm not a guitarist, so what's it called, the nut up at the top end of the fretboard. There's a little bar that the strings pass over. I think, is that called the nut? Anyway, whatever. The guitar string is attached and fixed down at two ends, and it's under tension, and you pluck it and it vibrates. Okay, so that's what we're studying. All right, a vibrating guitar string. Okay, or something like that. All right, so U of t is the position at time t. Okay, now the string is pinned down at the two ends. So U of 0t, namely the height at the left endpoint, is going to be 0 for all t, and the height at the right endpoint, which is when x is L, is going to be 0 for all t. So this is called, we call this a boundary condition. And then at time t, this is for t greater than or equal to 0. And then for all x between 0 and L, at time t equals 0, the position of the string is some initial position. We call this an initial condition. So f of x is some function. Here, I'll draw it here. F of x is the initial position of the string at time t equals 0. All right. So if you like took the guitar string, here, I'll gesture with my hands for a moment. So if you had this guitar string and you grabbed it in the middle and you pulled it, you stretched it up so that it was pulled out of position and held it there, then that curve, whatever that function is, that would be f of x. And then you let go, and then the string vibrates. Okay. Now you could also have the string in some initial position, and it could also have some initial velocity. Like you could hold the string in position, and then instead of just simply letting go, you like push it down. And so it has an initial velocity as well as an initial position. But for purposes of this first example, let's just not worry about that. Let's just suppose that the derivative with respect to time, that's the velocity, at each point is going to be 0 for all x. So let's just take the initial velocity to be 0. That'll just kind of simplify. Later on, we'll consider an initial position and an initial velocity. But for now, let's just worry about the initial position. Okay, all right. So this is the setup, and this is the setup. And so now there's an equation that models this physical situation, and I'll write it down. So the second partial of u with respect to t is equal to some constant times the second partial of u with respect to x. There's a lot of different notations for partial derivatives. Sometimes second partials are denoted using subscripts. So you might see something like u sub tt equals c squared u sub xx. That's the same thing. But anyway, so here it is, and this equation has a name. It's called the wave equation. All right, and it's the one-dimensional wave equation, the 1D wave equation, because we're just dealing with a string that goes along a single axis, and then it's vibrating in a perpendicular direction. The two-dimensional wave equation would be the model for a situation where you had a two-dimensional object that was spanning some region in the plane with some boundary curve, and it was under tension, and then you pulled that into some initial position and gave it some initial velocity and let it go, and it vibrated. So an example to have in mind there would be like the head of a drum, right? A drum consists of some membrane made of something, which is stretched over a frame, and then it vibrates when you hit it. So that's going to be modeled by the two-dimensional wave equation, and we'll solve that equation later. But let's just start with the 1D wave equation, which you could think of as a vibrating string. Yes, I see a hand up, Jeremy.
Yeah. So when you have written down the partial u xt equals 0 for 0 in between x and L. Are you saying the initial, you said that was the initial velocity, right?
The initial,
on the bottom right, on the bottom.
the initial position is u of x0, which we're calling f of x.
Yeah.
The initial velocity, which we'll denote later on, we'll call that g of x, but let's just assume that that's 0.
So that's the partial u at t equals 0?
Yeah. I see. Oh, I see. Yeah, I'm sorry. Yes, correct. Yes. That's the partial. Yes, that's the partial. All right. Yeah. It is at 0. Yeah, the initial velocity. Here, let me figure out a better way to write that. So it's the partial of u xt with respect to t. The derivative with respect to time is velocity, evaluated at t equals 0. How's that? Does that make more sense? Is that?
Yeah, thank you.
Yeah, I'm not talking about the derivative in the x direction. I'm talking about the derivative with respect to t, which is velocity, and then we just evaluate that. So it's the velocity, it's the vertical velocity of a point on the string at the very beginning. Okay, but we're assuming it's 0, right? So in other words, you're just holding the string in some fixed position, not moving, and then you let go of the string, and then it starts vibrating because it's under tension. Okay, and C is some constant that just depends on physical properties of the string. So C is a constant, so we're not really going to worry about it. It's just some constant that depends on the string itself. Like, for example, the string has a certain elasticity, which is a property of the string itself, and the string also is under tension. And so, if it's a guitar string, and you turn the I forget what it's called, the little knob that you turn to tighten the guitar string, that's going to increase the tension. And so C is a constant that just depends on those physical properties of the string, the elasticity, the tension, and I'm not sure what else, maybe. Okay, so that, yeah. Now this vibrating string satisfies this equation. Okay. Now, I'm not going to go through the derivation of this equation because that really is physics. Okay, so I'm going to leave that to your physics professors, or actually you can just read it in the book. It's sketched out in the book. It's not hard. But anyway, you can just read about that, and using classical mechanics, Newton's laws and whatnot. You can derive that this situation satisfies this equation. But we're just going to focus on the mathematics of solving this equation. Okay, so that's it. That's the problem. And all right. So does anybody have any questions so far about what we're interested, or what we're going to try to do? No questions. Okay. All right. Good. Okay. So now, so there's a whole sort of formal process we could go through at this point now to start coming up with solutions, and we'll do that later. It's called separation of variables and all that. But just for this introductory attempt to solve this thing, I want to be a little more informal. So I'm just going to sort of guess. I'm just going to guess what a solution might look like. Okay, so I don't think, it's too hard to sort of imagine that, one thing that could happen is, like, let's say you just pick the string up in the middle, grab it in the very center and pull it up and let go. And then it's just going to sort of vibrate like this, right? It's just going to vibrate like this. But you could also grab it at some point about a third of the way across, and then grab it at a second point that's about 2/3 of the way across, and pull one down and pull the other up and let go. And then it's going to undulate like this. And, so you can start to imagine all these different pictures of what this thing can look like, so just to kind of let's just draw a little picture of those. Okay, so I'll go back to here, and so here, let's just draw some pictures. So I'm just being really informal and intuitive here. So the string could go like this, and then, that could go down, and then that could go down, and then it could continue past the 0 level because it has momentum until it stretches all the way down to there. And then it could start going back up again. Or another case is it could, see, this is all going from 0 to L. It could go like this. And then it could sort of undulate or vibrate, starting from that position and so on. Or the next thing it could do is it could go like this. I could have 2 points, say, there, and it could go up like that, down like that, up like that. Okay, so let's call these n equals 1, n equals 2, n equals 3, and let's just write down what is this graph. This is the sine of n pi x over L, right? That's what this is. When n is 1, you have the sine of pi x over L. That's this function right here. That's u equals the sine of pi x over L. And then this one right here is u equals the sine of 2 pi x over L. And this one right here is u equals the sine of 3 pi x over L, etc. Here, in fact, let's call this u1, u2, u3, etc. So the sine of n pi x over L, which I'll call u n of x, is this graph. And those are just sort of intuitive guesses for what a solution might look like. Except this isn't a function of x and t yet. This is just a function of x. So this would just be like, this would be a description of the string at a particular snapshot. If we let time run, then it's going to be moving. And so what's this thing going to look like? Now, I just so happen to have a graphic of that. So let me just bring that up. It's not a very fancy graphic, but it's there. Let's see if I go to my web page, and then if I go to the web page for the course, which you hopefully have already taken a look at. I go down at the very bottom, some examples. Here is a picture of some fundamental modes of vibration of a string. Okay, can everybody see that? Can you see that?
Yeah.
Yeah.
Yes. Okay.
Yes.
Good. All right. Okay. All right. So there you go. So you see that's so this picture. So this picture indicates 1, 2, 3, 4, 5 different possible patterns of vibration of the string. The very first one, mode 1, you know, it's just going. It's just that's the first picture I drew. N equals 1. It's just going up and down. And then mode 2, it's got, and notice mode 2, there's a point right in the center at L/2 where it's not moving at all. And then on the left-hand side and on the right-hand side, it's going up and down, but they're exactly 180 degrees out of phase from one another. And then in mode 3, there are 2 points, one at the 1/3 spot and one at the 2/3 spot where it's not moving. And then in between, on those 3 intervals, it's moving up and down, but out of phase, and so on. Okay, so these are called fundamental modes of vibration of this string. And there's one of them for every positive integer n. And so those are solutions to the wave equation. Okay, now to write down the
Professor?
actual function, yes.
But would those other, when there's more than the 2 nodes at the endpoints, would those be additional boundary conditions or no?
Well, no, we're not imposing there. No, don't think of those as boundary conditions, because we're not, boundary conditions are things that we impose at the beginning of the problem. Okay, so at the beginning of the problem, we say that U is 0 at the left and the right hand endpoints. So those are our boundary conditions. And all the solutions that we look at have to satisfy those boundary conditions. All right, now it just so happens that some of the solutions satisfy further conditions of being stationary at various points, but some of them don't. And we want to consider all these solutions at once. We don't want to, right now, we want to consider all of them. We don't want to exclude any. So, you know, if you put in the condition that it also has to be stationary at L/2, then mode 2 would be a solution and mode 4 would be a solution, but then mode 1 and 3 wouldn't be solutions anymore, right? So, so let's not do that. Let's just stick with the left and right hand endpoint so that all of these solutions are going to be admissible. All right, does that make sense?
Yes, thank you.
Yeah, you could impose further boundary conditions if you wanted. But right now, and that would eliminate some of those solutions. But right now I'm just imposing these ones that we wrote down so that we're going to get all of those as solutions. Okay, so we have all these solutions. Now, well, but these are only the functions of X. We need to get them to vibrate. They're not moving yet. There's no T, right? They're not moving yet. Okay, so let's make them move. Okay, so what I need to do is I need to take this function sine n pi x over L, and then I need to multiply it by an amplitude, and that amplitude is now going to vary with time. So let me here, how shall I just say this? I'll just say it's a time varying amplitude. Okay, now again, if you go back to our picture, you see that the amplitude is varying, but it's also oscillating. It's varying sinusoidally or cosinusoidally with time, which kind of, it sort of would have to, right? Because it can't, you know, the amplitude can't be something like, you know, t squared. You know, t squared goes off to infinity as t goes to infinity. So if the amplitude was something like t squared, then in a matter of, you know, split second, the thing would fly off to infinity and the string would break. Okay, and we're not doing that. We're not breaking the string. We're just letting this. We just want the string to vibrate in a nice pattern like this. So the amplitude is also varying sinusoidally. So let's write down some function like that for the amplitude. So let me write down, I'll put down something like n pi. Now this is going to depend on t. So I'll put n pi ct over L as the amplitude. So we have a sine function in the x direction, which reflects the fact that the sort of the position of the string at any given moment is a sine curve. And then we have an amplitude in front of it, which in the time direction is also sinusoidal or cosinusoidal, indicating that the amplitude is fluctuating. So now we have a function of two variables. Let's call this x u of xt. And because it depends on n, we have one of these for every n. So I'll call this one u sub n. So n is 1, 2, 3, etc. Okay, so here's a function. All right. Now, how did I choose these constants? Well, the n pi x over L, that was sort of forced on us because we need this thing to fit, we need this thing to go on this interval from 0 to L, and we need it to be 0 at the endpoints. So that kind of forced these constants n pi over L in the second factor. But what about the first factor? I could put all kinds of constants in there and still get something that varies, oscillates harmonically. So how did I choose these constants? Well, I chose these constants because they make this thing work as a solution. So let's just verify that. That's just going to be a quick calculation. If we take the partial of this function that I wrote down here with respect to t, well, let's see, the derivative of the cosine is minus the sine. So I'm going to get minus the sine of n pi ct over L times, I have to bring this constant out front. So I get n pi c over L. And then this is times sine of n pi x over L. I'm taking the partial with respect to t. Okay, so the second factor just comes out. And then I do it again. So I'm going to have the second partial of u with respect to t. And now the derivative of the sine is the cosine. So I get the cosine of n pi ct over L. And then I have to bring the constant out again. So I get n pi c over L squared in front. And then I have sine of n pi x over L. Okay, so that's the second partial of u with respect to t, and I rigged these constants. I chose these constants so that I would get a certain number in front there, which you will see in a second is the number that I would want. Okay, so now if we go to the next page and do this for u, we're going to take the partial with respect to u. So we're just going to have the cosine of n pi c t over L there. And then the derivative of the sine is the cosine. So we'll have the cosine of n pi x over L, and the n pi over L comes out. Okay, then we differentiate a second time to get the second partial of u with respect to x. That's a typo. And we're going to get we still have n pi over L there, but another n pi over L is going to come out. So that's going to get squared. The derivative of the cosine is minus the sine. So the second factor will now be sine n pi x over L. And then this factor involving t is just sitting there. I'm taking the partial with respect to x, not t. So nothing's happening there. Okay, so we get that. So now if we just compare these two things, we see that they're exactly the same, except that the partial with respect to u, the partial with respect to t twice has an extra c squared in it that the partial with respect to u doesn't have. So in fact, what we're getting is that the second partial of u with respect to t squared, that came out to c squared times the second partial of u with respect to x squared. And that is the wave equation. All right, so we got a solution to the wave equation by sort of guessing, just kind of using our intuition and just thinking, physically, what does a guitar string look like when it vibrates? And this is the solution we came up with. Okay, now if you don't like this idea of, well, intuitively, hand wavingly, we came up with a solution, that's okay. We're, like I said, we are going to come up with a more systematic and mathematical way of deriving this solution, not by just guessing. So we'll do that later. And that's important. And, I think that'll be important for something like the heat equation, where I don't think you can guess the heat equation, the solution to the heat equation quite so readily. I don't think it's as obvious. I think the wave equation is more intuitive as far as just kind of guessing what the solutions look like. If you look at the heat equation and Laplace's equation and some other things, I don't think you're going to guess it. And you're certainly not going to guess what the solution to Schrodinger's equation looks like. If somebody says, write down an equation that describes the orbitals of electrons in an atom, you're not going to say, oh, well, I can tell just by looking at an atom that the orbitals are going to be shaped like this. That's ridiculous, right? You can't even see an atom, so never mind that. So we'll do this a little more systematically, but so this is a good start. Okay, any questions about this? Okay, so
to the next slide for just a split second.
Yeah, sure.
Thank you.
Okay, so a little bit of history. Back in the late 1700s, Fourier was very interested in this problem. He was also very interested in the heat equation and understanding the way heat spreads or diffuses through a medium. And Euler was also thinking about this, and several other people. Fourier and Euler were probably the two main people. Well, no, actually, that's not true. D'Alembert, there were a number of people, but anyway, Fourier worked a lot on this problem, and so he took this solution that we just wrote down. U sub n x of t is given by this product of this cosine and this sine, a function of two variables. And he observed, he said, well, if I take this for different values of n and add them all up, then that's going to also give me a solution, because the equation is linear. So let me take a linear combination of these solutions for various values of n. So I'll take u sub n xt and add these up. I'll take a linear combination of these. So the a sub n's are constants, and we're going to add up some finite number of these things. this is also a solution. And the reason is because the equation, the wave equation, the thing we're solving, the wave equation is a linear equation. All right, now I'm not going to get it, like I said, I didn't want to get into formal definitions or anything like this in this first lecture. So I'm not even going to bother right now to write down the definition of a linear equation. But I mean, if you just look at it, it's clear, right? I mean, you can just check, just differentiate and plug in and just check that if U1 and U2 are solutions to this equation, then any linear combination of them, A and B are constants here, is also a solution, right? You can just check that just by plugging into the equation. Okay, so we have this solution right here. Now Fourier took it one step further, and this is where he really went off the deep end and got labeled as a radical, and Euler had a conniption fit. What if we take an infinite sum of these solutions? So what if we just let capital N go to infinity and just take an infinite sum of these fundamental modes of vibration and add that up? Well, Fourier said that that's also a solution. And that was pretty radical. And a lot of people said, what? Okay. And that launched a whole debate, which lasted for hundreds of years and basically led to the entire development of real analysis. I've been teaching, and studying real analysis, but for many years I didn't really know that much about the history. But I've, more recently been looking at the history, and I've come to learn that this problem of solving the wave equation or the heat equation, which Fourier worked on and whose name is associated to that, was actually one of the fundamental problems that motivated the whole development of real analysis. Now, I just want to point out a couple things here. First of all, when you take an infinite sum of functions, you're getting an infinite series of functions. Now, you've already seen infinite series of functions, namely, you're familiar with power series. So power series are functions that are defined by taking a sum of infinitely many different functions, but the functions are polynomials. So a power series is an infinite polynomial. Okay, well, you don't have to stick to polynomials. You can take any sequence of functions and try to form an infinite sum. And what we're doing here is we're forming an infinite sum of trigonometric functions. So it's kind of like a power series, vaguely, and it's analogous in that it's an infinite sum of functions, but it's very different from a power series because instead of adding up polynomials, we're adding up infinitely many trigonometric functions. Okay, so that's what Fourier suggested. But he said, but this was only the start. He actually said something further, which was far more radical even than this. If you notice, when you go back to the finite sum, this is periodic, right? Because each one of these functions, for each n, each one of these functions is periodic. It has this one has period L, this one has period L over 2, this one has period L over 3, they're all periodic. And if I added a bunch of them up, then the sum, finitely many of them, the sum would also be periodic. It's just that its period would be, well, what would the period, let's see, what would the period of these three be? It would be periodic. If I took these three functions and added them up, what would the period be? Does anybody know? It wouldn't be L over 3, because this one isn't L over 3 periodic, and it wouldn't be L over 2, because this one isn't L over 2 periodic, but it would be what? Any ideas?
Over
Could be L over
6.
6.
How about, yeah, how about L over 6? It would be L over 6 periodic, because 6 is a multiple of 2 and 3, right? So if you had finitely many of these terms, you could take the multiple of all their periods, and that would give you a period for this. So this is periodic. So this solution is only going to be, this is periodic. Okay, well, if you add up infinitely many of them, then it's not periodic. So Fourier is saying that there are non-periodic solutions to this problem. And he went one step further, and this was the crazy part. Fourier said all solutions look like this. So he went one step further, and he basically said that every solution to this boundary value problem, this wave equation problem with these boundary conditions and these initial conditions, I'm assuming the special case where the initial velocity is 0, but you can consider non-zero initial velocity. But subject to those conditions, Fourier said that every solution has this form. And that was radical, and people rejected that. And Euler in particular said, well, you know, that's nonsense, because that would imply that every function is somehow an infinite sum of trigonometric functions. And that obviously isn't true. Well, it turns out it is. Every function is an infinite sum of trigonometric functions. So Fourier, in some sense that has to be made precise, was right. And so that is why we nowadays have Fourier analysis and Fourier series, which is what we're going to study. So it's an amazing, beautiful subject. It also, by the way, Fourier series and Fourier series are used for a lot of other things besides PDEs. They're not just good for solving PDEs. They're good for all kinds of things. But in particular, you know, they're one of the basic methods for solving PDEs, and it's the method we're going to focus on the most. So you could say you're taking an arbitrary vibration or an arbitrary sound wave, and you're breaking it down into its constituent fundamental components. And this is the basis for all audio science, music theory, electronics, digital signal processing, the visual system, the human auditory system, really, you could go on and on. So anyway, that's it. That's kind of that's a sort of a, I'm going to continue this on next time, because we're not done. We're not done. We have to, so the quick preview of what we have to do left is we have to actually solve the problem. We didn't really finish solving the problem. So we suppose we have the solution that looks like this. What are the coefficients? How do we actually solve for the a sub n's? And that depends on F, right? We had a specific boundary value problem with a specific function. That was the initial thing. So what we're going to do is we're going to use the function F to determine the actual a sub n's. It's going to turn out that the a sub n's are basically the Fourier coefficients of the Fourier series for the function f of x. So that's sort of part 2. This is really like part 1. Then we're going to do part 2, which will introduce us to Fourier series. We'll do that next time. All right. So, okay, does anybody have any questions or comments or anything?
When will you normally post the recording of class?
I will. I'm recording the class periods and I will be posting them. So the recordings of the class periods are going to be on the web page for the course. math.hunter.cuny.edu/Thompson/math301. But I'll try to put, I think I'm going to put over on the Blackboard page, I'll put a link to the math department, the website for the course, the web page for the course, so that you can click on that link and go over to them. But basically, that's where they're going to be. They're just going to be the recordings of class are going to be on the web page for the course. So
I think the question was, when are they going to be up, though? Do you have like a guesstimate of when you'll upload?
Oh, I'm sorry. When they're going to be up? Oh, well, I thought you said where. When? Well, the goal is going to be to try to get them up, shortly after class. I had that once I quit the Zoom session, Zoom has to, what happens is Zoom has to process this data and produce a file. And on my computer, it takes about 10 or 15 minutes to do that. And the problem is that I'm not just like going to sit here for 10 minutes and watch, paint dry. So it starts doing that. And then I go off and I do something else. And then unfortunately, that something else might end up, I don't know, I have a little, ADD thing going on. So I get back to it at some point, and then I have to remember to put it up. So I'll try to do it, as soon as I can, like hopefully like, later that evening or whatever. But if I forget, I know you could feel free to remind me. People will be reminding me. I will be getting emails from you saying, hey, you haven't posted today's class yet. Can you please put it up? I know that's going to happen. So anyway, feel free to remind me if it hasn't appeared yet. Okay, was that your question? Does that answer your question?
Yes, thank you.
Probably a long answer. I tend to give really long answers to questions. In fact, I'll just tell you quickly this one story. A few years ago, I discovered, I was noticing that people were saying, a lot of people started saying to me all the time, they say, oh, I have a quick question, I have a quick question. And everybody, colleagues, students, everybody's always saying, oh, Professor Thompson or Rob, hey, I have a quick question for you. And I couldn't figure out, why does everybody have such a quick question, And then one day, it just hit me. I just had an epiphany. I realized it's like when people say, I have a quick question, what they really mean is, I have a question. I just want a quick answer. That's what they're saying. That's what that means. I have a quick question means, please, dear God, just give me a quick answer. So I get it. I figured that out. Doesn't mean I can do it, but at least I understand the issue. Okay. Anything else? Any quick questions? All right. Okay, let's go. All right. So I also posted some homework problems. So, start working on those. And I'll see you next Tuesday, I guess. All right. Okay. All right. Bye.